Now, in this last chapter of this Control System 1 lecture, we want to talk about improvement of closed-loop systems. The idea behind this is the following, but before I start, note that in workbook the chapter number is 5.3. There is just a renumbering. I think you are not confused about this. Okay, the idea is, okay, there may be a loop with actuator, process, sensor, and you have designed a PID T1 controller with best phase margin, best pole compensation values, and so on. So you have optimized your PID controller, and more can a PID controller not do. And now in our example, the Z2 is too large. So the PID controller could not compensate Z2 fast enough, intensively enough, so that the user can accept the change of the difference between the desired and controlled value caused by this disturbance. So this is an example situation. We assume that Z2 is too large for this controller. Can we do with additional hardware, additional tricks, additional ideas? Can we do additional things to remove this problem with Z2? The answer is yes. There are several methods. I want to present 3 typical methods, which are also can be found in practical experience. And finally, I will end up in the cascaded control concept, so that you can see with cascaded loops we get very, very good performance of loops and can improve loop performance with small changes, small additions with a very high efficiency. So far, what we first can say is, why could a disturbance Z2 be too large? Because a PID controller could be very fast. The differentiator, if there is small changes, could advance react with large compensating changes here. But assume that a disturbance step appears here, then this step change has to run through FS3, run through FS4. Until then, X is changed, but then this change of X at once caused a reaction, but this reaction could be very fast due to the differentiator, but this reaction has to run through FS1 and through FS2, and only then the compensation can start. So the signal has to run through the complete loop before any reaction could affect and could compensate Z2. That is the problem of a single loop system. So the tricks based on the principle, can I shorten this way? Then I will be faster. Okay, the first trick comes with the next picture on workbook page. What page is this? It is the page 53. The chapter 5.3 is on page 53. There you can see the pages. In my numbering, chapter 5.3 is covered by the project number 4, the project with the integrator in the process. So the first idea is that what we call precontrol. What is this? Let's look for the next picture. Yeah, in this picture you see there is a change in the way of Z2. We have interrupted the way of Z2 with this summing point, have added a junction point and a block G sub Z with a negative feedback. So this is an additional loop, pre-control loop, with the following idea. Sometimes it is possible that we can interrupt the connection between the disturbance and the original loop by adding some hardware. Example, this could be the disturbance. No? Example of pre-control is following example. In the case that Z2 is change of supply software. Very often, the loop, the actuators and so on are supported with active additional supply voltage. And this supply voltage, if this comes out of an AC connector, for example, in our heating, in our temperature control system, the heating power depends on the voltage of the power plugs. And in Germany, we have a voltage of 230 volts plus and minus 10%. So it can be 207, but it can also be 243, 53. So there could be a change plus to minus 10-15%, and this can influence the behavior of the loop. The question is, how can we interrupt this way? In many applications, you know how we can do this with a stabilized power supply. Pre-control with stabilized power supply. Stabilized power supply. So we we add an actuator, for example, after the rectifier, an actuator, a transistor or linear controller. The output voltage then is measured, and with an internal controller, this transistor is controlled in that way that this voltage is constant. So here can be a change, and here is no change. So this is the idea of a stabilized power supply. And then this loop has nothing to do anymore with the change of the original power supply. And this can be just one IC in a semiconductor chip. Costs in low power, say 1 to 2 euros. Today, stabilized power supplies are available in any power range. That's one idea for pre-control. Second idea is Z2 is change of temperature. Now the ambient temperature can influence system behavior in many applications. For example, if you have a sinusoidal generator, then the temperature changes the base frequency quartz. Or if you have sensor principle, then you need a sensor, and many sensors also have a rather big temperature dependence. So it could be a good idea to isolate the ambient temperature from your system. This isolation can be done just with isolation, but there is a better idea with pre-control, which is used in some high quality devices. Z2 is change of temperature, and pre-control is done by heating the quartz or heating the sensor to a stabilized temperature. Yeah, I have seen this in Trägerwerk in Germany. There they have an oxygen sensor with high accuracy, and the oxygen sensor is heated to a temperature, say, to 60 degrees centigrade. The heating control loop holds this temperature constant, independent of the ambient temperature. So the sensor results are very stable and very accurate, and the measurement is done by independent of the ambient temperature. That is an idea of pre-control. Sometimes this doesn't work. Think about the following situation. If this is a speed control, say a hand drilling machine, that is the output of the tachometer sensor, the speed is controlled to a desired temperature. The main influence, the main disturbance of a speed control is the load, the torque of the motor. Z2 is the torque. Then imagine you want to prevent this torque from your speed control loop. It means you need here a second motor. Then the second motor has a problem, and the first motor, unloaded, is then working very properly, but this is not a very good help for the user because the situation now is transferred to the second motor. So sometimes the idea of pre-control doesn't work. Then, if this is not a good idea for your application, think about the second idea. Second idea is disturbance feedforward. That is the official expression. Disturbance feedforward. Note that here in our first idea, you need what is this? A summing point is nothing else than an actuator, an additional actuator, additional sensor for the result of your controlling, and an additional controller. The most expensive thing, I think, will be the second actuator. In the second idea of the disturbance feed forward, this is not necessary. You use the original available actuator, which is still in your loop, but you need two additional things. I take the picture from workbook. Note what happens now with Z2. Here Z2 has here junction point, no interruption. That means I measure Z2. So you need, that is the important thing, you need, if this is available, not too expensive, disturbance sensor additional. If you can afford an additional disturbance sensor, then take the disturbance signal, go through a compensation filter and add this signal directly with a negative sign into your signal coming out of the controller. This is normally a low power voltage signal. This is the actuator. So just this is an addition of two voltages, costs no money. You use now the available still paid actuator. The question is, what is the best compensation filter and why this could be faster in the reaction? The idea is, if there is a disturbance step, at once this signal can go into this disturbance filter, which is your design. So the response here could be very fast. A compensation signal is added with a negative sign to compensate. And this compensation signal then has only to run through FS1 and FS2 to compensate Z2 here. So if this filter is good, this is fast enough, Z2 doesn't influence the input of FF3, and X is unchanged. X is undisturbed. So this, the controller has at this time less work. And this is faster because the way is faster, shorter. The way is shorter. Way is shorter, and then you can better compensate the disturbance influence. Better, faster compensation is possible. Okay. Let's think about an optimal compensation filter GZ. The idea is we need to completely compensate Z2 effect here. We need here the negative Z2 signal. Negative Z2. If we have this there, then independent of this signal, automatically here appears the negative Z2 signal, and the result is 0. So then this is the ideal compensation with negative Z2. To get negative Z2, and here we have positive Z2, negative sign is here, this is possible if the product of GZ transfer function times fs1 times fs2 is 1. Yeah, ideal compensation. If GZ times fs1 times fs2 is 1, then if there is a signal, automatically here you have the negative same signal and the addition is 0 there. What does that mean? Ideal compensation means that you need a filter which is the inverse of the both blocks in front of the disturbance. Inverse filters. Inverse means if this is a low pass, you need a high pass. If this is a PT2, you need a notch filter. Yeah, PT2, if fs1 is k divided by 1 plus pt, then fs1 to the power of negative 1 is the inverse, is 1 plus pt divided by k. And this, what is this? This is a PD block. To compensate a PT1, you need a PD. In workbook page 16, I can open it quickly. Then there is a column we have never used before. This is the column for the inverse filters. Let's have a quick look of the types of the inverse filters in the workbook, page 16. Yeah, page 16 has here our name for our blocks. The PT1 inverse system is a PD. An integrator inverse is a differentiator. A differentiator inverse is an integrator. A typical block we have, the PD is the PT1, of course, you can turn it around. A PI inverse is a DT1, and so on. So finally, a biggest problem is if you have a delay time block, row 15, there is a empty cell because you cannot compensate a delay. So if there is a delay, it is not compensatable. Then you have to go with other ideas. In control system 2, I will show you a very good idea to compensate delay time blocks with Smith's predictor. This I think comes later in the next lecture. Okay, come back to PT1. The typical elements of processes are PT1s. We need PDs, but you know a PD, we have discussed this in one pre-chapter, the PD cannot be realized because a step at the input of a PD causes a direct impulse. Theoretically, of course, this cannot be realized with normal hardware, but you can also have an improvement if you use a PDT1. With the PDT1 you can not completely compensate the Z2, but nearly compensate the Z2, and that is also an improvement. Yeah, PD block with PDT1, you get not complete compensation, but improve behavior. That's the idea. Behavior, the disturbance behavior of the loop. So this idea helps if you can afford, find a sensor for this disturbance, then think about here compensation filter. This helps the PID. If there is some uncompensated Z2 here, the rest is to be done with the normal PID T1 controller you have designed. Yeah, this could be a help so that finally the specification is matched and the user is happy. If these methods are not working, not possible, a very powerful third idea comes now. Third idea. The idea is called cascaded loops. Before I start with this question, think about the idea if one PID T1, note that here the PID is a name, the block name, but of course we know behind the PID there is always a PID T1 because you can't realize a PID. If one PID T1 doesn't fulfill the specifications relating to Z2, what happens if I add a second one? Can a second PID improve behavior? First idea is the second integrator here cannot help, makes only the loop slow, and that is not an improvement, that is makes the behavior worse. Yeah? A second differentiator here cannot do the job because one differentiator here with large step depths caused large impulses here, and if you have worked with an optimal PID, then you have found an optimal step depth, and a second PD behind this with a second step depth, it cannot be an improvement because the big problem is not to have a fast PID. The big improvement is the way is too long. You have to shorten the way, and in this case you isolate Z2. The way is the same, but here you shorten the way. And in the cascaded loop, you also shorten the way for the reaction, but with a little different idea. So look for the picture of the cascaded loops, and then we show this in our next video. So this is video was number 63. Okay.